How's it going, everybody, and welcome back to another 1001 MSc online tutorial video. So my name is Brock Grant, and today we're going to be covering some of the questions regarding forces and Newton's law of motion. So just be aware that same with the previous set of videos, that this will be involving textbook 2. So we're going to be covering a variety of different questions here, so don't forget to just click the little annotations that can be found down here to fast forward the video to the particular question that you're wanting help with. Now again, I do recommend you go through video 1 for forces and Newton's laws, but also go through the kinematics in 1 dimension video 2 to show how I deconstruct the questions, and just be aware that these sort of topics are quite math heavy. So make sure that you recap on your math skills, rearranging math equations and so on. Okay, so let us start with question 1. So an aeroplane has a mass of 3.1 times 10 to the 4, and it takes off under the influence of a constant net force. So of 3.7 times 10 to the 4 newtons. So what is the net force that acts on the plane's 78 kilo pilot? So it wants the net force, but of the pilot. So the first thing that I do here, the first thing I think of is I go, okay, we've got force, we're given a mass, so the first thing I write down is F equals ma. So force is equal to mass times acceleration. So we know with our aeroplane that it has a mass of 3.1 times 10 to the 4 kilos, and that we are given a net force. Now because force is proportional to its mass, we need to look at the acceleration, because the acceleration of the aeroplane and the acceleration of the pilot will be the same. The only things that are changing here are obviously the mass of the two, the plane's a bit heavier, and the amount of force, because they're proportional. So what we can do here is, step 1 is we look at the acceleration for the plane. We go force is equal to mass times acceleration. So the airplane, after acceleration, so we look over here, the relationship is a multiply. So as this moves over, it's going to turn into a divide. So force over mass will equal to the acceleration. So we have our force, which is 3.7 times 10 to the 4 newtons, divided by the mass. So the mass is 3.1 times 10 to the 4 kilograms. So this means that the acceleration is going to be 1.19 meters per second squared, okay, by punching that into your calculator. So we know that the acceleration for both the plane and the pilot is going to be 1.19 meters per second squared. So now we can use this value to calculate the net force on the pilot. So again, we use force for the pilot is equal to ma. So the force, we don't know, that's what we want, is equal to the mass. So the pilot is 78 kilos, multiplied by the acceleration, which is 1.19 meters per second squared. So we go 78 times 1.19, and that is going to give us a total force of 92.82 newtons. And that is our final answer. So again, it's being able to have that ability to understand the question, see what's going on. Okay, so this is where it requires that knowledge of knowing that the force and the amount of mass is proportional to each other. So let us now move on to question 3. So, 2 horizontal forces are acting on a box. Now, if you have your textbook, I recommend going to this question, because there is actually a picture there that will help you. So F2 can point either left or right. So we're going to have like a box. And we have F1 that's going to be pointing this way. So F1 is plus 9 newtons. So we can see that here. But we don't know where F2 is. And the mass of the box is 3 kilos. So we know that this is 3 kilos. Find the magnitude. So remember, that just means how much. and the direction of F2 when the box is. So if the box is A, moving at 5 meters per second squared. So what we have to do here, so let's look at, so we've got A, B, and C. Now we're going to be assuming no friction throughout this entire question, so we don't want to unnecessarily complicate things. So for A, we have an acceleration of 5 meters per second, because it's 5 meters per second squared. So what we do is we go, the sum of forces is equal to mass times acceleration. So the sum of the forces is the mass, which is 3 kilos, times acceleration, which is 5 meters per second squared. So 5 times 3, it means the sum of our force is equal to 15 newtons in the right direction. Now, we know that F1 is giving us 9 newtons. So that means that F2 is going to equal to 6 newtons. So 15 minus 9 newtons, which is F1, is going to give us 6 newtons. Okay, let us look at B. So the acceleration is now negative 5 meters per second squared. So same deal, we go sum of forces is equal to mass times acceleration. So we know all of the force is equal to the mass, which is going to be 3 kilos, multiplied by the acceleration, which is negative 5 meters per second squared, which means the sum of the forces is going to equal to negative 15 newtons. So what this means is that we have, so the sum of our forces, so we're going to have 15 minus, so we're going to have negative 15 newtons minus our 9 newtons, that is from our F1, which means that F2 is going to equal to negative 24 newtons. So what we can see here is that for this box to have an acceleration of 5 meters per second, F2 only needs to be 6 newtons. Why? Because F1 and F2 are working together. They're both pushing in the same direction. However, when we've got negative 5 meters per second squared, what's going on is we've got F2 that is going in the opposite direction. This means that F2 must be negative 24 newtons, because not only does it need to have enough force to push the box in the opposite direction, but it also needs to have enough force to overcome the F1, because F1 is still pushing in that one direction by 9 newtons. But F2 has to both counteract that F1 and push it backwards with enough force to accelerate the box by 5 meters per second squared in the opposite direction. Okay, and the very last one, if the acceleration is 0 meters per second squared. So this is a nice easy one, assuming you know your Newton's laws of motion. Because if something has 0 acceleration, it means either one of two things. It's either at a constant speed or it's at rest. It's not moving at all. So for the purpose of this question, we're going to assume it's at rest because it's not accelerating. So because it's not accelerating, it means the sum of all forces must equal to 0. So if we know that F1 is pushing this direction at plus 9 newtons, it means that F2 must be pushing this way at negative 9 newtons. Because imagine it's like a tug of war. It's like how we were describing polarity, how they're doing that tug of war. For this to be absolutely stationary, F2 must pull at the exact same force as F1. And that is why the summary, or the amount of force of these two will be 0, resulting in 0 acceleration. Okay, let us now have a look at question 7. So, a 1,580 kilo car is traveling with a speed of 15 meters per second. what is the magnitude of the horizontal net force that is required to bring the car to a halt at a distance of 50 meters? Okay, so we were given a couple of very important things here. We were given the mass. We were also given the initial velocity is 15 meters per second. We were given the final velocity because it said to a halt, so it means the final velocity is 0. We were also given the displacement. However, we have no idea of the acceleration, or in this case, deacceleration. Now, I may hear you going, oh, hang on, Brock, this is kinematics. We did this last time. This is where they can blur these modules together, such as chemistry, how it can overcome and combine different modules. Guess what? You can do it with physics, and it's even easier to tie them together in physics because it's all related. So, what we need to do is we need to put our kinematics cap on, and we need to go, well, what are our 5 variables? So we've got mass, initial and final velocity, displacement, acceleration is the only one we don't know. So then we go horizontal net force. Well, hang on. So net force. So that is force is equal to mass times acceleration. There's our link. Acceleration, acceleration. So that is the key to join these two things together. So what we do is we need to calculate our total acceleration here because we don't have time, but that's okay because we don't need time. So what we do is we can use v squared is equal to VO squared plus 2AX. So what we can do is we can rearrange this. So we're going to have v squared minus VO squared divided by, so multiply and a multiply, so that's going to be 2x is equal to the acceleration. So we have our final velocity, which was 0, minus our initial velocity, which is 15, divided by 2 times x, so our displacement was 50 meters, so it's going to be 2 times 50, is going to give us our acceleration. So our acceleration is going to equal to negative 2.25 meters per second squared. So we have our acceleration now, so that's part 1 done. Part 2 is we can now use our acceleration in our force is equal to ma equation. So F equals ma. So it means our force is going to equal to the mass, which is 1580 kilos, multiplied by the acceleration, which is going to be negative 2.25 meters per second squared, which means that the total force is going to be negative 3,560 newtons. So what does that mean? That means that if the car is moving this direction with a speed of 15 meters per second, if we want this car to stop in a distance of 50 meters, we need to have a countering force. So we need to have acceleration moving this way at 3,560 newtons. So all it means is, by that negative, it means that it is accelerating in the opposite direction to the velocity. Okay, it's moving in the opposite way. So that tells us, which we could have deduced by ourselves, is that the car is deaccelerating. Okay, so let us now have a look at question 31. So, the mass of a robot is 5,450 kilos. So, okay, cool, mad. This robot weighs 3,620 newtons more on planet A than it does on planet B. Okay, that is interesting, because what's jumping out at me so far is they're talking about planets. Now, it's quite customary for us to make assumptions based on things we know about, well, Earth. So the fact that we're looking at different planets is putting me a bit on edge right now, so I know I need to pay particular attention and be careful with what assumptions I make. So, both planets have the same radius, okay, so that's awesome, of 1.33 times 10 to the 7 meters. Okay, so that means that we're seeing both planets are the same sort of size. What is the difference, so just MA minus MB, in the masses of these planets? Okay, so they want the mass of the planets. Now, something else that's jumping to my attention is they don't want to know the specific mass of planet A or the specific mass of planet B. They're not interested. They want to know the difference between them. So that is interesting. And we are given a little bit of sort of random information here and there. So let's have a look here. So I've got the mass of a particular robot. So mass is 5,450 kilos. Now another thing that's interesting too is that it says weighs. Okay. So it said the mass of a robot is 5,450 kilos, but it's saying it weighs more on one than the other. Okay, so two things are jumping out at me there as well. First one is, again, this is a difference, and secondly, we're looking at weight. So remember, weight is equal to mass times gravity. So weight, that's fine, okay? The mass, awesome. But this is where we're getting into trouble, is gravity. So normally I would look at gravity and go, awesome, it's 9.8 meters per second squared, happy days. But because we saw on here planets, we cannot assume they're going to have the same gravity as Earth. So we cannot make that assumption here. So what I can do is I know that the weight on A, so the weight on planet A minus the weight on planet B is going to equal to 3,620 newtons. Because it says it weighs this much more on A than B. So again, this is a difference. So we're seeing a bit of a theme here. We're focusing on the difference between. So both planets have the same radius. Okay, so I'm going to go radius. And again, it's asking for the difference between. Okay, so it's looking for the difference between the two masses of these planets. Okay, so what I'm seeing here is, again, we need to focus on looking at our gravity. We know that the weight on planet A minus the weight on planet B is 3,620 newtons. So I'm going to start there. So how I do that is I know that weight is mass times gravity. However, the difference here is in the gravity. So I know that the force of gravity is G m1 m2 over r squared. Now again, don't worry, it's not expected for you to have that memorized. Okay, you don't need that. It will be provided to you in the exam. Again, weight is caused by gravity. So we can write this as the weight of planet A is equal to G m1 m2 over r squared. And we can do the exact same thing with the weight of planet B. Now, what we can do here is, we know that it's mass 1, mass 2. So what have we got here? We've got the mass 1. So I'm going to replace that with the mass of planet A times object number 2. So the mass of object number 2, which is going to be our robot. Because we have the mass of the planet and the mass of the robot, because that's where the weight is coming from. So that's how we can compare the two. These are the two objects that have that force of attraction. And we've got the mass of planet B times the mass of the robot. So these two m's here are the exact same because we're looking at the same robot. So this means that we can substitute these two formulas here into this. So we know that the weight on planet A, which is going to be, okay, so this is essentially this exact same formula here. So the gravitational constant, again, that will be provided for you. So that's going to be our G. So we have the mass of A, which we don't know, but we do know the mass here. We know the mass here. We know the mass, we don't know the mass of B. Now, the interesting thing is radius, okay? Now, I know that's not radius because I said that in the previous video that R represents distance, not radius. But we are comparing the mass of an object compared to the mass of that planet. So in this case, radius and the distance are one and the same. They sort of, that's how it works. So in this example, and this is probably the only one I've really seen that has it like this, the radius is indeed the distance between these two objects. Because remembering, radius is from the core to the surface. This little robot is on the surface. So the radius is the distance between the robot and the planet. Now, what we can do here is we can do some sneaky little rearranging here because we have a lot of double ups because both planets have the same radius. So this radius is the same as this radius. And we've got the mass of the robot. So this mass is the same as this mass. So what we can do is we have gravity is multiplied by MA and M. Then we've got gravity is multiplied by mass B times M. So it's the same operations, and then the overall product of these two are going to be subtracted by each other. So a simpler way that we can write this is we can go gravity times mass, which is gravity times mass. So we can see that already, divided by R squared. So we've got R squared. So these two are the exact same. So that's fine. That's all good. And then we multiply this by mass A minus mass B. So that is how this can be simplified to this. So we can just rearrange to isolate this. Okay, so we rearrange this by going 3620. So we've got our radius, which is a divide. So that's going to turn into a multiply. And then we're going to have our G and M, so gravity, constant, and our mass of the robot. So that's going to turn into a divide. So we're going to have, so that's going to give us this rearranged formula as we can see here. Now we just need to substitute our values that we have. So MA minus MB, we don't know that, that's the point of the question, is equal to, so we're going to have 3620 multiplied by R squared. So remembering that the distance between these two, which in this case is indeed the radius, is going to be 1.33 times 10 to the 7 squared. So our gravitational constant is 6.67 times 10 to the power of negative 11. Now don't worry, again, you don't need to memorize that. Multiplied by the mass. So this is the mass of the robot. So we're going to multiply this by 5,450 kilograms. So we simplify this, so we've got 3,620 times by 1.33 times 10 to the 7 squared. So don't forget it's squared. So that's going to give us 6.4 times 10 to the 17 divided by the multiplication of these two, which is going to give us 3.64 times 10 to the negative 7. Okay, so now we simply just need to divide these two and we're going to have our answer. So we pop this into the calculator and we know that the MA minus MB is going to give us 1.76 times 10 to the 24 kilograms. That is the difference in mass of the two planets. So again, we look at this number and we go, does it make sense? Does it fit? Now, we're referring to the size of a planet. So these things are huge, okay? They're bloody heavy. So 1.76 times 10 to the 24 kilos? Yeah, I would believe that. If it said like times 10 to the 3, probably not, because that's like a ton. So in short, this is how we were able to use weight and the fact that we're on different planets by using the same robot to calculate the difference in mass between those two planets. Okay, so a person is trying to judge whether a picture, so we've got a picture that has a mass of 1.1 kilograms, is properly positioned by pressing it onto a wall. We've got a bit of a wall here, and someone is trying to press a photo frame onto the wall. So the pressing force is perpendicular to the wall. Okay, so that's perpendicular. So we've got our wall here, 90 degrees. That's the pressing force. Now the coefficient of static friction between the picture and the wall is 0.66. Now that is a massive hint if I've ever seen one. So we know that the coefficient for static friction is going to equal to 0.660. So they basically just told us one of the formulas that we need to use. So this is between the picture and the wall, so that's here. What is the minimum amount of pressing force that must be used? Okay, so basically what the question is asking is, how much force do we need to press here to make sure that this picture stays up? Because remember, with friction, the greater the perpendicular force, or the force normal, the greater the amount of friction. So the first thing I'm going to do here is I'm going to write down my friction formula. But we can see a bit of a problem here. So here is the force normal, and that is what the question is asking for, because it's asking for the amount of pressing force. So that's fine, that's cool. Now, the coefficient of static, so the static coefficient, we have been given. Sweet. So what's the amount of friction that we have? Well, we don't know. But we can find out, because we want to apply enough force onto this picture frame here to stop it from moving. So if we want to stop it from moving, remember that is the sum of all forces is equal to 0. So we need to look at this and go, well, okay, what forces do we have in play here? So we do have our pressing force, but that is not relating to its overall movements, because we're going to have a pressing force here, but that just means we're going to have a force normal coming out here. So that's not really necessary. That's not important. So we look at our other axis. What do we have going on here? So we know that there is a force pushing this frame downwards, which is gravity. So remembering that the weight of something, which is the force inflicted on an object due to gravity, is the weight. So this is mass times gravity. Now, because we want this to be stationary, we don't want it to be moving. So this means that the amount of friction force coming upwards must be equal to the amount of force pushing downwards. Because if there was a greater amount of friction, it would be moving up the wall. If there was a greater amount of weight, so mass times gravity, it would be moving down. So what we do here is we have a look. So we've got F equals ma, so force, mass, acceleration. So we want to know the force, because this force is going to be our frictional force, is equal to the mass. So we were told the mass here, so it was 1.10 kilograms, multiplied by the acceleration. So it's fair to say that we're on Earth. So we're going to multiply this by 9.8 meters per second squared, which means the force of the static friction is going to be 10.78 newtons. So we are wanting to calculate the force normal. So our force due to friction is going to be 10.78 newtons. And we know that the coefficient of static friction is 0.660, and that's going to equal our force normal. So 10.78 divided by 0.660 is going to give us 16.3 newtons. So what this means is that for this picture frame to stay on the wall, we will need to apply 16.3 newtons of force to ensure that the friction will be high enough to counteract the weight, which is the mass times gravity, and make sure that the sum of all those forces are equal to 0 and the picture frame stays on the wall.